Hello, class. Okay, so let's say we have a solenoid here that's creating a magnetic field. Let's say it's out of the page. And let's say the magnetic field is changing. So again, if there's like let's say we put a ring here, like a conducting ring, we know that we're going to get an induced current in that ring. But what if we don't have a ring here? Let's just remember the EMF that's around some closed path. So let's say we just draw this path here, and we have an EMF, and so we know there has to be an electric field. Now, if there was a conductor that would drive a current, it would require an electric field. And let's just say at one point on the ring, the electric field looks like this. Now, this actually cannot be the case, but let's examine why that can't be the case. So imagine that we had an electric field that looked like this. And we could break it up into two components, one that's tangential and one that's radial. However, this radial component cannot exist. So we have this solenoid. This is a cross-section coming out of the board. What if we draw a Gaussian cylinder here, parallel to the solenoid? And we know from Gauss's law that the flux through this surface, this is just a cross-section, it's actually a cylinder, but we know that the flux through this surface has to be equal to the charge enclosed over epsilon naught. This is the electric flux we're talking about here. And but the charge enclosed is zero. We're saying there's nothing inside this solenoid, and so the electric flux has to be zero. And if we have a radial component outwards, then there would be a flux. Now, just to be clear, we're making some assumptions about symmetry. Like, what if the electric field was like this? What if over here, we had an electric flux inwards? Then these two could cancel out, and we could still have zero electric flux. If at some point we had a radial component outwards, but at other points we had a radial component inwards. So we can't conclude just because the electric flux is zero that the radial component of the electric field must be zero. However, because we have this perfect symmetry, we just have a circle here, there's no way we can have some parts that are outwards and some parts that are inward from symmetry. And so from that, we can conclude that the radial component of the electric field must be zero. And so if an electric field exists, which we know it must by Faraday's law, they have to be circular. So we have this circular electric field. Of course, that's, I'm just going to draw it going this way. Again, this only exists because there is a changing magnetic field. So I kind of just decided something right now. I'm going to give you an extra credit problem. So that's kind of a reward for actually watching the videos, which hopefully you're doing. So the question is, sorry, let me write this down, extra credit. Is the magnetic field increasing or decreasing? So we know the magnetic field is out of the board, And it has to be changing to create this flux, the changing flux, which will then create this EMF. And so just by giving you the direction of the current, does that mean the magnetic field is increasing or decreasing? So this is a Lenz's law problem. So I'm going to put I'll put a quiz on Canvas where I'm just going to tell you, it's just going to be a simple multiple choice. Based on the problem in the lecture, is the magnetic field increasing or decreasing? And, in magnitude. And so again, that's an incentive to watch the video. Okay, but let's get back here. Now, this is actually a remarkable thing. We have this electric field that's moving around, and this is something that we have never seen before. Because before, we've talked about static charges. Nothing is moving. We have just charges, point charges. Or we can have a continuous charge distribution. We know how to calculate electric fields. And basically, we know that electric fields, they follow this idea of linear superposition. But if you just look at a single point charge or a dipole, let's just say we have one charge, positive charge, the electric field lines move away, radially outwards. And these lines, if all we have is a positive charge, these lines just have to keep moving forever. They can't stop. Like, what if we get really far away and you say, well, this line has to stop somewhere? Let's just say it stops right there. Okay, let's apply Gauss's law. Let's draw a surface around here, and we know that the flux, if that electric field line just stops, then the flux is, well, it doesn't equal zero. We can say it's less than zero, because the electric field line is going this way, and so we have a negative flux, which means there must be a negative charge inside there. So these electric field lines, they start on positive charges and they have to end on negative charges. And that's been the case for everything that we've talked about so far. And really, in a sense, it's almost like there's nothing new here, because we have a current that's creating this magnetic field. And we can picture that current as just a bunch of charges. Like we have a wire going through this solenoid, and just think of it as charges that are moving, and now they're giving rise to these circular electric field lines that form closed loops. And again, this is something that is not possible with static charges. It can only happen if we have moving charges. And so this is something entirely new. And very interesting thing that they form these closed loops. So let's look at the EMF. So let's say we place a charge here, like a test charge here, and we move it around this loop here. Now, the work done by the electric field, so there's going to be, let's say it's a positive test charge, and we're moving it around a circle. So remember, the work is force times distance. Well, really a dot product though. But in this case, the force and velocity are always in the same direction. So the work in this case is just going to be the force times the distance. Actually, I'd prefer to write it F times D. And the force is just the charge times the electric field. And here we have Q naught E times the distance. We're going around one loop. So the distance is 2 pi r. Now remember the EMF is defined as the work done on a test charge divided by the charge. So it's the work done by the electric field divided by the charge. So if we look at the EMF, we just divide by Q naught, we get E times the circumference, or just the distance that it moved, which would be the circumference of the circle. So the EMF is E times the circumference of the circle. And again, that's just in this particular case when we're going through a circular path and we have circular electric fields. But in general, the EMF, we can write that as a line integral. So we would basically just do the same thing in a more general path. So the EMF in general, we just look at like the work, which we'd write as this line integral, and when you divide by the charge, we'd get this result. And so we can write Faraday's law in a different form now. So I'm going to erase this. This is just nothing new. It's an old definition. So what we have is the integral of E dot ds is equal to minus the change in magnetic flux over time. So again, in order to apply Faraday's law, we need some path. It has to be a closed path, which is why we draw that circle around it. And then we can look at the magnetic flux through that path that we define in order to apply Faraday's law. And again, that applies to any reasonable closed path that we pick. Faraday's law applies. And so in this form, this is one of the I'm going to put a box around this. Very, very important. This is called Faraday's law, and this is one of Maxwell's equations. Might sound strange, it's Faraday's law. Why are we calling it Maxwell's equation? Who's Maxwell, anyways? Well, it turns out that there's 4 laws. Actually, we're kind of done now, in a sense. We talked about Gauss's law. There's actually 2 Gauss's law. So we have Gauss that the flux is equal to Q over epsilon naught. That's the electric flux. Gauss's law for magnetic flux is that the flux is 0. Magnetic flux around any closed volume is 0, which is the no magnetic monopole rule. We have Ampere's law. That and now we have Faraday's law. Which we could write this way. Okay, so again, 2 laws with Gauss's name on them, Ampere's law and Faraday's law. And these were all figured out before Maxwell even entered the picture. So who's Maxwell? Maxwell actually discovered, he kind of discovered in 2 different ways that there's something wrong here. This is actually not something we really talk about in this class, but it's very important anyways. But there's something wrong with these laws. Now, Maxwell was a brilliant mathematical physicist. He knew, physicists did not know as much math back. This was the late 1800s, where physics was much more experimentally based. You do experiments and you learn about things, but expressing things mathematically, yeah, that was done, but there wasn't quite as much emphasis. Like Faraday himself, for instance, had no formal mathematical training, and he was one of the greatest physicists of all time. But yeah, physics has become much more mathematical. It's taught that way much more. But anyways, Maxwell was a brilliant mathematician, and he knew that there was an inconsistency in these equations, which we're not going to get into. But he also discovered on physical grounds that this cannot make sense. And so what Maxwell did, what he found specifically is that Ampere's law is missing something. And Maxwell fixed that. And basically that's it. So these four laws existed before Maxwell came around, and he discovered a problem in one of them, and he fixed it, and so they named the whole set of equations after him. Now, kind of an interesting story. There's a physicist named Richard Feynman. He died in like the 1990s or so not that long ago. But he was one of the greatest physicists of all times. And what Richard Feynman said is that Maxwell discovering, it's called Maxwell's displacement current. That's how he fixed this. He said he did that in 1895. And what Feynman said is that Maxwell's discovery of the displacement current is the most important thing that happened in the 19th century. And he wasn't talking about most important thing in physics or even in science. Just out of literally everything that happened in the 19th century, Maxwell's discovery was the single most important thing that happened. So it was a very, very big deal when he fixed these. And so that's why this whole set of equations is named after him. They're called Maxwell's equations. And basically, to the subject of classical electromagnetism, Maxwell's equations are essentially like Newton's laws. They give a complete description of classical electromagnetism. Okay, but I want to go back and just talk a little more about this because this is also something kind of new. We talked about electric fields, and we always say that they are conservative. And conservative means, like say we take this charge and move it in a closed path, then the net work done by that force has to be zero. However, if we move this charge, remember the work done on some closed path, we integrate the force over the path. And again, if we're looking at the electric force, that's just Q times the electric field. And in order for this the electric force to be conservative, then it has to be zero. The work around any closed path has to be zero. And that is clearly not the case any longer. Here, the work is just Q times this. And again, if there is a changing magnetic flux present, then this electric field is no longer conservative, and we can't define a simple potential function like we did before. So we're actually dealing with a non-conservative situation right now. And so that's something to definitely be careful about. The idea of conservative and non-conservative, it's extremely important. But in electrostatics, if the charges are fixed, then, they can, if the charges are fixed, it's not going to be a magnetic field at all. Or if we have charges moving in a certain predictable way, then you can have a magnetic flux, but not a changing magnetic flux. But generally speaking, once charges are moving, then we can no longer define an electric potential quite so easily. So we have to be a little careful about that. The electric potential was basically just this integral E dot ds, but now that has to be seen as a special case where the magnetic flux is not changing. So in general, we have to go back to this full version of Faraday's law. So if the magnetic flux is constant, or zero, which is also constant, then we can just define our simple our electric potential. But we have to be a little bit more careful now that we're dealing with situations with magnetic fields where we can have changing fluxes. Okay, so I think that's it for this video. We'll do some examples in class, but yeah, that'll be it for Faraday's law right now. All right.